Number 1. So what are the units of rate constant for the rate expression for the following chemical equation? So we have this equation here. We have the rate law. So we're being asked for what are the units of the rate constant K. Now for units, this is just a dimensional analysis. The key thing here, for all rates, no matter what the order of the rate is, the rate of a reaction is molar per second, and big M over S. So this means that molar per second equals, I'll put an open parenthesis, a blank parenthesis for K, because we're going to try to figure that out, times whatever else we got here. So here we have this NO squared is the concentration of NO squared, so molar squared. And then we have Cl2, which is just concentration of Cl2, so molar again. So we have here molar over seconds has to equal something times molar cubed. That's it. So the only way to make this work is we put, it has to be over seconds. And then we have, this is going to be molar cubed, so we need molar on the top. So this would be molar squared on the bottom, right? So if you have 1 over molar squared per second, that gives you these molars would cancel out with these two, and you'd have a single molar on the top and a single seconds on the bottom. So that's how you can figure out the unit from the dimensional analysis. So that leads us to the answer of, well, this says in moles per liter. Now, we know that molarity is moles per liter, so they make it a little bit more difficult. So from this 1 over m squared times seconds, it's the same thing as, let me write it down here, 1 over mole squared per liter squared per second. And if you do that math a little bit, the liter squared goes to the top, the mole squared stays on the bottom. So it's liters squared per mole squared times seconds. That would be D. Okay, moving on to number 2. Which of the following factors does not change with temperature? So with temperature, we understand that the temperature goes up, the rate of the reaction increases. This can tell us a lot. That's all we need to know. It happens faster. So the half-life, meaning the time it takes for the reaction to go through half of its amount, or half of its reactant. That means, well, if you increase the temperature, getting to the half-life or getting to the halfway point will happen faster. So yeah, the half-life does change with temperature. The rate constant, yeah, the reaction's going faster, so the rate constant changes. The overall reaction rate changes. The rate order, that might also change, because if you increase temperature, that might introduce some other kinetics to the reactants hitting together to change the order. But the activation energy does not change. Just because the reaction goes faster, that doesn't mean the activation energy threshold. So that's, if you remember the energy diagram, that's this barrier right here. That doesn't change. But the time it takes to get there obviously will be less, and it will be faster to get there, but that threshold does not change with temperature. Okay, next, a decomposition reaction with a rate that is observed to slow down as the reaction proceeds. This means, so every phrase here is there to help us. So if the rate slows down as the reaction goes on, that means the rate is dependent on the concentration of the reactant. That means it is either first order or second order, not zero order. Remember zero order? If you look at reactant versus time, it looks like a straight line. So the amount of reactant does not change that slope. Even if it's a low amount of reactant, it'll decrease in a linear manner. First or second order, they decrease like this. So they have a dependence on the concentration of reactant. And it has a half-life that does not depend on the initial concentration. Now, we know that from, I know my class knows that, where you have first order. First order, that's where you have the half-life, T1/2 equals natural log of 2 over K, right? So this means that there's no initial concentration here. So it does not depend on initial concentration, or the half-life doesn't. So we know this is first order. And this information is given to us on the exam. It will be given on the final as well, because we see the integrated rate laws here, which we can deduce that half-life formula from. So this means, so which of the statements is true? So we know it's first order. So basically it's asking us which of the following statements are true for first order. So a plot of initial concentration as a function of time is linear. That's not true. We know for first order it's natural log. So a plot of natural log versus time is linear. So B is correct. All right, next. Use the following information regarding the reaction mechanism for questions 4 to 6. So reaction mechanisms, we know that when we have an elementary step, not the overall reaction, when we have an elementary step, that means we can take the slow step, which is the rate determining step, and we can come up with a rate law. And this rate law is representative of the entire rate of the reaction, of the rate law of the overall reaction, I should say. So this means that rate equals K for the slow step times C squared times B, like that. So this is what we can say about the rate determining step, the slow step. There is some manipulation involved. So for the fast equilibrium step, we can make the rate going forward equal to the rate going backwards, which would be K times A equals K minus 1 times B times C. So we can say that as well. So from that, let's see what we can figure out. So what is the rate law of the rate determining step? Well, we just figured that out, right? The slow step is C squared times B. So that's this one, C squared times B. What is the overall reaction? Now for overall reaction, we have to add all of these together. So if we add these together, we have A. Does any A cancel out? We have another A here. So we have A and A. So if we add these up, we have so far 2A. What happens to B? We have a B on the right, a B on the left. Those cancel out. And then we have a B on the right. So then we have B on the right. Let's look at C. C, we have 1 on the right, 2 on the left, 1 on the right. So the C's will all cancel out. And then D, we have 1 on the right, 1 on the left. So they cancel out. So that means we have 2A yields B. That's the total reaction. So whenever we have an overall or a total reaction, it's simply just adding the reactions together. So that's C. All right, step 1 has an equilibrium constant of K1. How would the equilibrium constant K2 of 2B plus 2C yields 2A be expressed in terms of K1? So let's do something here. Let's take, this is A. So step 1 is A yields B plus C. So we have A yields B plus C. Now this is represented by K1 as the equilibrium constant. Now we are manipulating this reaction. We're saying, all right, if you have 2B plus 2C yields 2A, that means you're multiplying everything by 2 and you're flipping it. So if we multiply by 2, we take K1 and we square it. If we flip it, we're taking it to the negative 1, so 1 over that. So the new K is going to be equal to 1 over K1 squared, which is the same thing as K2 equals K1 to the negative 2, which is D. So important to know how manipulating a chemical reaction, multiplying it, flipping it, changes the equilibrium constant. It doesn't just, oh, you multiply it by 2 if you multiply the reaction by 2. No, you take it to the second power. If you flip the reaction, you don't just simply make K negative, because K can't be negative. You make K 1 over itself. So these are important things to know, and you should go back and study from. All right, next. The following reaction is exothermic. Off the bat, exothermic means we got heat on the right side. So we know that off the bat. And remember what I said during class, for those of you who had me, is to treat heat like a reactant or a product, just like you would any of these chemicals when we're talking about Le Chatelier's principle. So which change will affect the equilibrium, will shift the equilibrium to the left? If you raise the temperature, that means if we treat heat like a product, raising this temperature, it will go to the left. So that one is true. By adding SO3, will tip the balance to the right side. To undo that, it wants to go to the left. So that's true. Off the bat, you know, because those first two are true, it's probably all the above. So you can kind of save time that way. And the third choice, removing O2. If we remove this O2, it becomes light on the left side. So to replenish that O2, again, it has to go to the left. So D is the correct answer. All right, number 8. Consider the following reaction. A reaction mixture initially contains copper sulfide and 2.9 molar O2. Determine the equilibrium constant of O2, or equilibrium concentration of O2 if Kc is 1.5. All right, so for this reaction, we have to do an ice chart. because we have some gases. And we want to figure out some equilibrium concentrations here. So we have Cu plus SO2. And the states are important here because we know that in equilibrium expressions, solids and liquids don't count. Remember, it's only gases and aqueous. So our K expression for this is going to be equal. Well, I'm going to get rid of that for a second. We have to write our ice chart. Our K expression, K equals SO2 divided by O2. Since those are the only gases, the copper and the copper sulfide don't matter. And you notice I'm using Christmas colors? That was intentional. So ice chart. Initial concentration of O2 is 2.9. For SO2, it's 0. Then we are going to be losing some O2. It will be converted to SO2. 2.9 minus X, and then we have X. Then we can simply plug that into the equilibrium expression. We get K divided by 2.9 minus X. Sorry, I said K. X divided by 2.9 minus X equals 1.5, which is the K value that's given from right here. And you can solve for X and get something. That something is not the answer. So the question is, determine the equilibrium concentration of O2. So whatever we get for X here, and somebody could feel free to put it in the chat, if whatever you get for X, if you're following along, whatever that X is, 2.9 minus that X is the O2 concentration at equilibrium. So that's what you're looking for. And I guarantee that X is probably one of the answer choices to throw you off. So, but the answer would be 2.9 minus X. So it's important to understand what they're asking for. And to read it carefully. Determine the equilibrium concentration. That's what you're determining here. All right. So while you guys are figuring that out, I'll go on to number 9. And actually, if you don't figure it out, that's fine, because for those watching that are going to be watching on YouTube after I post this, you can pause the video and solve it yourself. So that's a good thing for you guys to do. Number 9. So in which of the following reactions is Kc equal Kp? Now we have that equation, Kp equals Kc times RT to the delta N. And delta N is the key factor here because it is the change in moles, products minus reactants. So what this means is that the only way Kp will equal Kc is if delta N is equal to 0, meaning the number of gas moles on the left side of the reaction is the same as the right. So we can simply count gas moles. So for A, we have 7 on the left, 8 on the right. So they won't be equal. They'll be different. For B, you have 4 on the left, 4 on the right. That's good. So that's your answer. And then C doesn't work. You have 6 and 4, and then you have 9 and 6. Okay. So B is your answer. Next. Number 10, the equilibrium constant is given for 2 reactions below. Determine the value of the missing constant. So we want to manipulate these 2 equations to give us the third one, and then see how those K values work together. So it's kind of like Hess's law from chapter 7 of Chem 1. So we want 2 A's on the left, right? So let's say we have equation 1, equation 2. We want, and we'll call this one F for final. So we want 2 A's on the left. In equation 2, we have 2 A's on the left. So automatically, we're not manipulating the second equation at all. So this is going to be, this Kc value is equal to 28.2. It will not change. Next, we have 1 B on the left. Okay, this one also has a B on the left. Okay. Oh, but this one has 2 B. Right. So this one, and then the final one also has A2B on the right. Now, reaction 1 has A2B on the left. So that means this top reaction 1 would have to be flipped. If it's flipped, our A2B ends up on the right side like it's supposed to, and also our B ends up on the right side. That's good, because we'll have 1 B on the right side, 2 B's on the left, so that would cancel out to make 1 B on the left. So if we were to flip this reaction, and remember, flipping the equilibrium constant is the same as taking it to the -1. So 16.4 to the -1 would be equal to the new Kc. And then since we're adding these reactions together, Remember, if you add two reactions, their K equilibrium constants multiply together. They don't add together. It's not like enthalpy with Hess's law. So 16.4 to the -1 for the first Kc after it's modified times 28.2. So it's basically 28.2 divided by 16.4. It's around 1 point something, so I guess 1.72 is the answer. Okay, number 11. Express the equilibrium constant in the following reaction. So here we have solids on the right, we have three gases on the left, and we have solids on the left here. So really the only thing that we care about is this oxygen. So it'll be 1 over O2 cubed. That's it. And we're not going to have 3 O2 cubed. Are these answers the same? B and C are the same. Interesting. So that's how you know it's wrong. So D would be the right answer. Because so this is not solubility. For solubility, chapter 18, I believe, the end of chapter 18, this is where we would say 3 times the molar solubility, cube all of that. That is how you determine it using the ice chart. But for simple equilibrium expressions, we don't do that. All right, next. Number 12, consider the following reaction at equilibrium. What effect will increasing the temperature have on the system? Now, whenever you have a question of what effect on equilibrium will it have, always think Le Chatelier's principle. When you're given exothermic or endothermic, in this case endothermic because delta H is positive, you can put in heat and use heat as a reactant or a product. So we know that it's endothermic, meaning heat is in the reactant side, and the products will take in the heat. They won't release it. So if we increase temperature, that means we're increasing the heat on the left, the reaction will go to the right to dissipate that heat. So the reaction will shift to the left. No. The equilibrium constant will decrease or increase. No, it won't. So the equilibrium constant stays the same. It only changes when we change pressure. So those are incorrect. And then D is correct because the reaction will shift to the right in the direction of the products. Next, 13. Which of the following statements concerning the relative reaction rates is correct? Now, this question several of you had difficulty with on the exam. Basically, it's how do we compare, using the molar ratios, how do we compare the rate of appearance or disappearance of substances? And what I showed my class in the chapter 15 slides is we can simply say that for any rate of a reactant, we could say the rate of the reaction equals -1 over the coefficient of the reactant times the change in reactant over change in time, which also equals the positive, meaning appearance, of 1 over the coefficient of the product times delta product over delta time. And this means that let's look at the answer choices now. The rate of disappearance of N2 equals 1/4 of the rate of appearance of formation of NH3. Now that just doesn't make any sense because it's not a 1 to 2, or it's not a 1 to 4 or a 4 to 1. It's a 1 to 2. So that's automatically wrong. So we don't even have to go over that one. The rate of disappearance of N2, it equals the rate of formation of NH3. Well, we know they're not equal because for every 1 mole of N2 that disappears, 2 moles of NH3 are formed. And even just saying that sentence and going through the logic in your head, it should bring you right to the answer because I just said it, right? I just said the association right there, which is for every 1 mole of N2 that disappears, 2 moles of NH3 are formed, meaning the rate of formation of NH3 is double that of N2. So that's incorrect there for C. For B, for C, the rate of disappearance of N2 is twice the rate of formation of NH3. No, I just said it's the opposite. The rate of appearance of NH3 is double that of N2. And then D, the rate of disappearance of N2 is 3 times the rate of disappearance of H3. So that's incorrect because we know that H3 has to decrease at 3 times the rate of N2 in order to keep up with N2. So E will be right. So the rate of disappearance of N2 is 1/3 the rate of disappearance of H2. So I'm thinking about that for a second. Wait, for every 1 mole of N2, 3 moles of H2. Yeah, so that means the rate of H2 is 3 times that of N2. So if that's the case, then 1/3 the rate of N2 is the same as H2, right? So yeah, this question was tough. It's a lot. It's a brain scrambler. So yeah, but definitely walk through the molar ratio, and that'll help you. All right, number 14, a possible reaction mechanism for the reaction of nitrogen dioxide with carbon monoxide is the following. What is the overall reaction and the most probable rate law? So overall reaction, we simply just add these together. So let's see, we have NO2. This NO2 would cancel out. This NO2, we would have NO2, just one NO2. Then for other reactants, we have NO3 on the left in equation 2. That would actually cancel out with NO3 on the right with equation 1. So that doesn't exist there. Then we have CO. There's no CO on the right. Then we have yields. Then we have NO. There's no NO on the left. And then plus CO2. So this is what the reaction would be. And that is choices A, B, and C. So we're between A, B, and C. Now, what we know about the reaction rate, or the rate law, is that we can only determine it from the slow step, right? So the slow step is the rate determining step. And from this, we can say that rate equals K times NO2 squared, right? That's what we can tell. If we had a fast equilibrium step, we can say that the rate law going forward equals the rate law going backwards, and we can find that and plug it in. But we don't have that information. It's just a one-way reaction for the fast. So we know that the rate equals K NO2 squared. That's all we can say. So the answer would be B. All right, 15. Yeah, rate law is a good question. So rate law is only just reactants. So you never include products in a rate law. But you do include the products when we do the equilibrium constant. That's chapter 16. All right, next. So the value of the equilibrium constant K depends on what? So we know that K is products over reactants, right? And it changes with temperature, because if you change the temperature of the system, you could have a different ratio depending on how fast it goes. Because if we know that, well, also, yeah. So yeah, the temperature changes everything. So temperature, the phases of the reactants, so that matters, because if you have solids, liquids, or gases, solids and liquids are not included in the value expression of K. So we know that the rate constant depends on the phases. The concentrations of products, of course, and reactants, yep, they're in the equation. So everything, all 4 of these matter. So the answer would be E. There was a version of this question that I made where I put for 3 and 4 the initial concentrations, and that threw some students off. I think that was the actual one on the exam, because I changed it at the last minute, because this was, I thought this was too easy. But we know the initial concentrations of reactant does not change the equilibrium constant, no matter how high or how low, because at the end of when equilibrium occurs, there will be a balance between reactants and products. So, and this balance will be the same ratio no matter how much of it you have. All right, consider the following potential energy diagram. Which letter shows activation energy of the catalyzed reaction? So that means this dotted line, a catalyst lowers the activation energy. So going from the start, which starts at right here, that's not a straight line, but it should be, to that dotted line, which is E. So E is the correct answer for the activation energy of the catalyzed reaction. All right, next. The elementary step for the catalyzed reaction is shown below. Identify the catalyst and identify the reactive intermediate. So the difference between an intermediate and a catalyst, they might be both canceled out, but a catalyst is present in the beginning, or sorry, not necessarily in the beginning. It's present in the end because it is not consumed in the reaction. The intermediate is canceled out in the middle, and it is consumed in the reaction. That's the only difference. So looking at these, we have IO minus. IO minus is in the right here. It's in the left here. So it cancels out, and there's no more IO minus. So that means it's an intermediate. So the intermediate is IO minus, which is here. Now, catalyst, I minus. Look at I minus. It starts out in the reaction, but it's not consumed, meaning it's not changed into something else, and it still ends up in the product. So we have I minus as the catalyst. Next, consider the chemical system at equilibrium. The reaction is exothermic, meaning it releases heat, as written, and the temperature of the system is raised. Which of the following will occur? So if you have an exothermic, meaning it releases heat, so you have reactants yields products plus I'll put Q for heat. So this means if I think I made a mistake before. I think I said that the equilibrium constant doesn't change with temperature. It does. Because it just shifts everything over. Okay, it does. So here's what we can say based on that. So we can say that because we're increasing heat, if we raise the temperature of the reaction, so increase the heat, it will move the reaction towards the reactant side, because we want to dissipate that heat and go to the place of less heat. So that means we have more reactants and less products. So that means the value of K will go from high to low. So it'll go lower. So the equilibrium shifts to the left and K will decrease. So that's D. All right, next, number 19. So which of the following changes to the equilibrium system above will increase the amount of HI in the equilibrium mixture? So again, La Chatelier's principle. So delta H is positive. That means it is endothermic, meaning the heat is in the reactants. So if we add H2, we're looking for a change that will increase the amount of HI. HI is right here. So we want it to move to the right. Increasing H2, yes, that'll go to the right. Increasing temperature, increasing heat, yep, that'll go to the right. Decreasing the pressure. Now, if we decrease pressure, what happens? If we decrease that pressure, the system will be at too low of a pressure, meaning it will want to increase its pressure. The way to increase its pressure is to go to the direction of the most gas moles. But in this case, the reaction has 2 moles of gas on the left, 2 moles of gas on the right. So there'll be no change. So decreasing the pressure definitely won't change it in either direction. So the answer will be 1 and 2. So that's C. All right, moving on. Number 20, the effect of a catalyst. We're decreasing activation energy, so enable an alternative path for the reaction with lower activation barrier. Yep, that's it. A catalyst may not, so this was kind of difficult. So some of you were confused between A and E. So increase the frequency of collisions between the reactants and products. This is not necessarily true. Temperature does this. It will make the molecules move faster to hit each other more frequently. But the catalyst doesn't. It just kind of brings them, well, biological catalyst could do that. It could, well, no, sorry. It brings them closer together. It doesn't increase the frequency of their collisions. It just makes the collisions easier, if that makes sense. So it's a little bit nuanced, but temperature is the factor that increases their frequency of collision. All right, now for these, I'm not going to solve all of them because they'll be integrated rate laws, but I'll at least get you on the right track to solving them on your own, either later on or now if you want. So 21, first order reaction has a half-life of 4.54. So off the bat, we know that the half-life is equal to natural log of 2 over K. So we can figure out K. How much time is required for the reactant to be reduced to 6.25% of its initial concentration. Now, the wording here is important. So 6.25% of its original. So if we start out with 1, going down to B 6.5% is 0.0625. It's not 0.9375, right? We are reducing it to 6.25% of the original amount. So integrated rate law, we can plug all this in. We know the integrated rate law is a natural log of A, which equals negative KT plus natural log of A0. We have A, which is our final, 0.0625 equals negative K. Now, K can be found from the natural log of 2 divided by 4.25. That's K, so negative K. We're looking for T plus the natural log of A0, which is 1. Natural log of 1 is 0. So it would just be simply this. And you could solve for T pretty easily. Does anyone have a value for T? If not, it's okay. All right, so yeah, you guys can work on that one. All right, number 22. Consider the first order decomposition reaction. At 500 Kelvin, the rate constant is 2.34. So it's first order again. So we know the rate constant. So automatically we know the half-life. We can use that as well. So how much time is needed for the reactant concentration to decay from 0.34 to 0.12? So in these questions, whenever they're asking about time with rate constants and with rates and rate constants and reactions, always think integrated rate law, because that's the only one that has time. The normal rate law, like the K times A times B, that doesn't involve time at all. So it's not really going to help us. So since it's first order, let's again write the first order integrated rate law. And this will be given to you. All right. Initial concentration, we have it. 0.34, final is 0.21. We have the rate constant. Rate constant is 2.34. And we're looking for time. That's it. Very easy. So natural log of our final concentration, which is 0.21, equals negative K. Our rate constant is 2.34 times temperature plus natural log of A0, which is 0.34. And that's it. And then you solve for T. And also, to answer that question, if you read the question carefully for number 21, it's not reduced by 6.25%. It's reduced to 6.25% of its original initial concentration. That means we're going to 0.0625, not 0.9375. So the wording is crucial. Okay. So, and also, Michael, thank you. So 18.1 for no question 21. So 18 point. Okay, nice. Thank you. All right, number 23. Apparently, when I was doing this, I got, so it says Patrick got 1.78 because we go through the exams together. And I think the answer wasn't here, and I got something different. But I'll show you how. And I think we did change it when we made the real exam. But anyway, so for the second order reaction, we have the second order reaction. What is the half-life when the initial NO concentration is 1.0 molar and the rate constant is 0.56 at 350 Kelvin? So the half-life for a second order, let me just look it up real quick. And even if you don't know it, you'll still be so if we look at the information that's going to be given to you, we can figure it out. So we have the integrated rate law right here for second order. You can simply take the A initial and A final and make well, you can put in their initial value. Hold on. So let's see, what is the initial values? Yeah, the initial value is 1. And what's the half-life? So if you plug in to the integrated rate law right here, you plug in 1 to A initial and 0.5 to A, and then you solve for T, that'll get your half-life. So that works every single time. So I'll write both ways. So we have 1 over A equals KT plus 1 over A0. So every single time, if you can do that. So if you plug in 1 over initial is 1, so K, whoops, K is already given as 0.56 times T, we're looking for that half-life, plus 1 over 1 equals 1 over 0.5. So you can solve for T there. The other way to do it is if you memorize your T half-lives for your 0, first, and second order, this simply becomes 1 over A0 times K. So A0 is 1.0, and then K is 0.56. And those should both be equal, and you should get the same answer for them. So it's basically 1, my calculator up, 1 divided by 0.56. That's like 1.78. So, yep, that's why I got 1.78. Okay, moving on. So number 24, suppose the rate of the reaction is second order for A equals B plus C. What is the approximate concentration of A after 55 seconds? So same thing, second order integrated rate law. It's right here, so we can kind of just plug it in. So what is the approximate concentration of A? We don't know A final, but we do know the rate constant of 0.035. We know the time, 55 seconds, plus 1 over the initial concentration, which is 0.80. And we can kind of plug and chug and solve for A. And that'll give us our answer. Next, number 25. For the first order reaction, the half-life is 15 seconds. What is the initial rate when A equals 0.5? So it's first order. This means, so then we have the half-life. Now for this, we're not given any initial and final, well, we have initial concentration, but we're not given any final concentration. So we cannot use the integrated rate law because we would kind of get stuck. So what we would do is use the normal rate law, the non-integrated rate law, where you have K times A, like this. So we know it's first order, and it's first order with respect to A. So this equation is actually right. So it's asking for what is the rate when we have a half-life of 15 and A is 0.5. So we'll put in 0.5 right here. Now we need to find this K value. Thank you, Tariq. Thank you. But 0.3 for that one. So we are looking for this K value. Now, since it's first order, we know that T1/2 equals natural log of 2 over K. So we have the half-life is 15. So we can do natural log of 2. So that's 0.693 divided by 15. And that gives a K value of 0.0462. We plug that into here, multiply that by 0.5, and we get 0.023, which is equal to D. Good. Next, 26. So carbon-14 is a half-life of 5,700 years, and it's first order. If a piece of wood has converted 88.5% of its carbon to carbon-14, then how old is it? So if 88% is already converted, that means how much is left? That's the remainder would be left. In this case, we have to just, again, like the other one before, we need to read the question carefully. So it's first order. So we know natural log of A final. So A final is actually 100 minus 88.5, which is 11.5, equals negative K. And so we have our half-life of 5,700 years. So 57 to 0 equals natural log of 2 over K. We can do 0.693 divided by 5720, and we get the K value is 1.21 times 10 to the negative fourth. So this equals 1.21 times 10 to the negative fourth. And that's going to be, we're looking for how old is it? So we don't know our t value. T is going to be in years, and then plus the natural log of A0. A0 would be 100. Because we say that if 88% of it is gone, we have 11.5. So then we have start out with 100. Or we can start out with 1 and do 0.115. Same thing. And then you can solve for t, and this will get your answer. All right, moving on. So 27, determine the rate law and the value for K for the following reaction for the data. So this kind of shifted over a little bit, but if you can imagine, this column goes for the first reactant, this column's for the second, this column's for the rate. Now, what we can say here is we can do a analysis of keeping one of the reactants constant while changing the other and seeing the effect on the rate. So it's called the experimental way of determining the rate law. So if we look at S2O8, for trial 2 and 3, we keep it constant, and then we decrease the other, the I minus, by half. And what does that do? It decreases the rate by half. If the rate moves the same way as the concentration, so this one decreases by half, the rate decreases by half, we can say it's first order with respect to I minus. So I minus, we'll just put a 1 on the top. Now, for trial 1 and 2, we keep I minus constant. S2O8 changes by like 1.5-ish. What happens to this rate? What happens to the rate? It goes from, if we do 6.65 divided by 4.54, that's about 1.5-ish, right? 1.46. So that means if you increase the concentration of this reactant A, the S2O8, by 1.5, the rate also increases by 1.5. That means it is first order with respect to that other reactant as well. So it's first order with respect to both. And that leads us to answer choice A or B only. And yeah, because it's that easy, we don't even have to find the rate constant. But we can very easily. Because we know it's first order with both, we can pick any trial. Let's pick trial 1. We know the concentrations and the rate. So the rate of the overall reaction would be 4.54, which equals K, times the S2O8 concentration, which is 0.3, times the I minus, which is 0.42. And this should get you K equals 36. All right, moving on. 3 more left. So consider the following reaction. A reaction mixture initially contains all of that. Determine the equilibrium pressure of NO2 and if Kp is 0.0118. So this screams ice chart. So we're going to write down the reaction again. The way I know it's an ice chart is because we're being asked for equilibrium concentrations. That's the dead giveaway. And we're being given a equilibrium constant or concentrations. So NO is going to be 0.86. And I know we're given ATM and pressure, but we can still determine the Kp value, right? And it's given us our Kp value, which has to be in terms of pressure anyway. So we have our products are 0, minus x, plus x. We end up with x squared divided by 0.86 minus x whole thing squared. That's going to equal our Kp value of 0.0118. All right, and then we can solve for x here. We can take the square root of that, get rid of these squares, and then you can solve it. All right, next, 29. So the reaction of C4H10 to C2H blah, 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 all that has an activation energy of 350. And the EA of the reverse reaction is 260. Estimate the enthalpy change for the reaction written above. All right, the best way to approach this is to write an energy diagram. So the activation energy of the forward reaction, let's just do that, is 350. So write this. This is 350. The EA of the reverse reaction is 260. So this means if we go reverse, meaning here back this way, we have 260, like this. Estimate the enthalpy change for the reaction written above, meaning what is the enthalpy difference from here to here, from start to finish in the forward reaction. So basically asking us to find the difference in these two values. So 350 minus 260 is 90. Now the question, is it plus 90 or minus 90? Well, because this works out where the reverse reaction requires less energy, that means the forward reaction gets to a place of higher energy, meaning it's endothermic, and B is the answer, so it's positive. All right, last one. Sodium carbonate, Na2CO3, can be prepared by heating sodium bicarbonate, and as shown below. So at 100 degrees Celsius, a 100-gram sample is placed in an evacuated sealed container and allowed to attain equilibrium. What is the final pressure? Okay, so this question is asking for, I remember a lot of you guys had problems with this one. It's asking for the final pressure in the container, not the equilibrium pressure, not the X value after you do the ice chart. Final pressure. This means you're adding all the pressures together after we do the ice chart. So I'm going to write down the ice chart. So it would be 2 NaHCO3 solid yields Na2CO3 solid plus CO2 gas plus H2O gas. All right, so now we have solids here, so we don't care about those. So we have no reactants. So our initial is going to be 0 across the board. Then we have plus X, and then we have X and X. So we have X squared. That's it. So our CO2 times the H2O, that is going to be all we need for our equilibrium expression. And it's going to be equal to Kp. Kp is 0.23. So the square root of 0.23, square root, that's going to be equal to X is, thank you, 0.48. Good. So now this represents the X value, right? If we plug X back into the equilibrium expressions right here for equilibrium pressures, we get 0.48. Now 0.48 is an answer choice, but that's not the answer. The question is, what is the final pressure in the container? So 0.48 plus 0.48, because there are two gases, the CO2 and the H2O, in the vessel at equilibrium. So the answer will actually be B, 0.96.